Hi, I'm Zeng. I would like to introduce our work on semantic linking maps for active visual object search. This work has been developed in the ProgressLab from University of Michigan. To start with, our objective is to enable a robot to effectively search for a previously unseen object in our daily environment. In this example, the robot is searching for a cup. It first navigates in the environment to an automatically selected view pose. And once it navigates there, it takes an observation of the environment. In this case, it detected a refrigerator and a sink. Because it knows that a common spatial relation could happen between the cup and the sink as well as the refrigerator, it's motivated to go closely and to examine that sink area. So in the end, it finds a cup in that area and retrieves the mug to the user. A core aspect of our approach is to exploit the inter-object spatial relations for object search. For example, when looking for a cup, the robot can exploit the knowledge about common spatial relations between the cup and the sink, between the cup and a refrigerator. More specifically, the cup can be inside a sink or it can be next to the sink. And the cup can be next to a refrigerator as well. And in our work, we probabilistically model the spatial relations between different pairs of objects. Compared to existing works, we have developed finer-grained spatial relations between objects. For example, we model the in, on, and next to relations between objects compared to coarse co-occurrences as modeled in previous works. While considering the probabilistic spatial dependencies between objects, we propose semantic linking maps, in short SLIM, to maintain a belief over objects' locations. Note that we're not just maintaining a belief over the target object, but we're also maintaining the belief over other objects, which we call landmarks. And we do not assume any prior knowledge on where those landmark objects can be in the environment. In addition, we also propose a hybrid search strategy to help select the robot view pose during the search process. The intuition behind this hybrid search strategy is to encourage the robot to explore promised regions that could contain the target objects, but what's more is to also explore promised regions that could contain landmark objects. Taking this looking for a cup, for example. If the robot can also explore regions that could contain a sink or a refrigerator, once it detected a sink or a refrigerator, it can help quickly narrow down the search region for look for the cup. Now let's walk through our approach using the previous real-world robot experiment. Again, the robot is tasked to find a cup. We assume a metric map of the environment is given, and we know the room types. In this case, on the left side is a living room, on the right side is a kitchen. We use semantic linking maps to maintain the belief over objects' locations. Note that we use particles to represent the belief over objects' locations. For each object, we will have a designated set of particles to represent possible locations of it. Initially, we draw particles for each object uniformly across the metric map. Here, we're showing SLIM updating the locations of objects based on dependencies between objects as well as the dependencies between object and rooms. Different color is representing different objects. Once we finish SLIM update, we fit Gaussian mixture models to the particles that represent the possible locations of the target object. And the number of the Gaussian mixtures are automatically selected based on expectation maximization method. And in order to sample possible view pose for the robot to navigate to, for each Gaussian component, we sample a set of view pose surrounding the Gaussian component by having the robot looking at the center of each Gaussian component. In this case, we are visualizing a set of sampled view poses in the red arrows. And in order to select which is the best view pose among the sampled poses. Previous works have used an utility function to rank each of these view poses and uses the one that was the maximum utility. In particular, the utility function is composed mainly by two terms. One is concerned about the confidence of finding the object in that region. In this case, it's noted by the weight of the Gaussian component. The other term in that utility function is concerned about the efforts for the robot to navigate to that pose. So it's a trade-off between these two terms. And we call this exploitation because the robot is basically looking for confident regions that contain a target object, in the meantime trying to minimize the efforts it needs to pay for the navigation. Compared to previous method, we propose hybrid search, in the sense that we also encourage the robot to explore regions that can contain other landmark objects. This additional term in this utility function adds the weight to the view poses that would lead the robot to explore promised regions that could contain landmark objects. And based on our proposed utility function, the robot can select the best view pose with the maximum utility score and then navigate towards there. Once it's there, it takes another observation and update the object locations accordingly through SLIM. It finds a refrigerator and a sink. After the SLIM update, as we can see in the sink area on the top right corner, because the robot knows that a cup can frequently occur in the sink or next to a sink, so you can see the hypothesis of the cup being there start to emerge around the sink area. And we go through the next Gaussian mixture model fitting and sampling and selecting view pose process, and this is the resulting next view pose that the robot decides to go, which leads to the robot to examine the sink area more closely. The robot has successfully found a cup around that sink area. We also quantitatively evaluated our methods compared to existing methods in a simulation experiment. It's an apartment-like environment, and we task the robot to find various objects such as coffee machine, laptop, cup across the environment. And just to give you a qualitative comparison between existing works and our work, what we're showing here is the trajectory that the robot traveled during the search. From left to right, the first 4 columns are the existing methods, and the last column is our method. In contrast to these existing methods, our work does not assume any prior knowledge on landmark objects, and our work also encouraged the robot to explore promised regions that can contain the target object, but also regions that can contain the landmark objects. And as we can see qualitatively, the search path resulting from our method is much more effective than the search path resulting from the existing methods. We also did quantitative evaluations on our method versus these existing methods on searching for objects in the same simulation environment, and we have shown that our method consistently outperforms the other existing methods. And please refer to our paper for the details on those quantitative evaluations. Here is another real-world experiment to show the efficacy of our proposed search strategy. Initially, the robot failed to navigate the first selected view pose because there is too much traffic going on. Once the traffic is resolved, it navigates towards the sink area to look for the cup. But this time the cup is not around the sink area. So the SLIM updated the belief of the cup locations, and it motivates the robot to look at the other side of the room. And by exploiting the inter-object spatial relations, the robot again successfully finds the target object. Thank you for your interest, and let me know if you have any questions through the Slack channel.